What I thought I'd do is do 4 very, very common moment and shear diagrams, and it'll serve as practice, but also these are very important ones that you should know. And so the first one we're going to do is a simply supported beam with a uniform load of W. And these are so important, I'm going to do them in variables, not with numbers, and therefore you could use these over and over. This type of beam that has a pin and a roller on the two ends has zero moment at the two ends, and we call this simply supported. I don't know why it's called simply supported. I guess because there's no moments on the two ends and it's the simplest way to support a beam. But we always say simply supported for this. I'm going to just do the statics for you. The total load is the area of that rectangle, which is W times L. It's symmetric, so you get half on each side. Okay, let's take a cut, close the loop, and set this distance to X. I'm going to redraw the free body diagram. Okay. There's the distance X. Here's this load W. That reaction is WL over 2. And the resultant force is the area of that rectangle, or W times X. And it's at the center of the rectangle, which is X over 2. Next, we need to draw in the shear and the moment in the positive sense. Remember, down on the right is positive for shear, and smiley is positive for moment. Now we're just going to use statics to solve for V and M. We'll take sum Fy equals 0, up is positive. That reaction WL over 2 is going up. The resultant of the rectangular load, Wx, is going down, so minus Wx. And the shear, even though it's in its positive sense, is down on the right, and down is negative for statics. That will all equal 0. Solving for V, we get WL over 2 minus Wx. Next, we're going to take some moments about the cut equals 0, counterclockwise as positive. This will give us M. The reason we take the moment around the cut, it eliminates shear from the equation, and I don't want to put in that shear equation. Okay, taking moments about the cut, that WL over 2 has a perpendicular distance of X from the cut. It's going clockwise around the cut, so negative. We have that Wx, which is the resultant of that rectangular load, and its distance is X over 2. It's going counterclockwise around the cut, so plus. And finally, we do have that moment M, counterclockwise around the cut, or around anywhere, equals 0. Solving for M, we get WL over 2 times X minus Wx squared over 2. Now let's plot these two functions, V and M, as functions of X. Traditionally, when you plot the shear and moment diagrams, you plot them directly below a picture of the beam with the load on it. So I've drawn it ahead of time. Let me just paste it here for you. There we go. So there's the beam with its load. And what I'm going to do next is I'm going to plot V. So if I plot V, which is, the function is WL over 2 minus W times X, the function will look like this. It will start off at WL over 2 when X is 0. And when you plug in all the way at the end, X is L, you get negative WL over 2. And if you look at that function, it's linear in x, so it'll be a straight line. Next, let's plot the moment diagram, or the moment plot. When you plug in x equals 0 into the equation for the moment, it turns out to be 0. Interestingly, when you plug in x's L, you get WL squared over 2 minus WL squared over 2, which is also 0. And when you plug in x's L over 2, halfway over, you get WL squared over 4 minus WL squared over 8, which will be WL squared over 8. And it's a parabola. It's minus x squared over 2 times w plus WL over 2x. And you get that.